So far this week, we've learned a lot about linear regression as a way to understand the linear relationships between two quantitative variables. Now, one thing we could ask is whether the two variables are really well described by a linear relationship. Now, we know some things about that already. For example, we know the r squared, the coefficient of determination, to measure how much of the variability in y is explained by the linear relationship with x. And we know about hypothesis testing to test whether or not the slope is equal to 0 or is not equal to 0 when comparing y to x. But we could still ask whether there's other things about the relationship between y and x that are not captured by the linear relationship. So let's consider some examples of that. For the first one, let's consider what we'll come to regard as an ideal case. So here we have a bunch of different points. Again, there's different x values and different y values. And the graph looks kind of linear, and that's the first thing you should always do is look at the graph and see if it's linear. Then, of course, we can use our formulas or get the computer to plot a line of best fit, the linear regression line. And there it is, and we see it appears to describe the data fairly well. But then we can also look at the residuals. Now remember, the residuals are the difference between the actual values of y that we see and the values that we would see along that line of best fit. So if we transform this graph into a graph of the residuals, then we're just seeing how far apart these yi's are from the line. And this is an ideal case because it's not because the y's are all exactly on the line, there's always some uncertainty involved, but it's because there's no particular pattern in the residuals. We've taken out the linear relationship, and what we have left is just kind of independent random errors for each of the different observations. So some of them are above the line, some of them are below the line, but whether the x value is smaller or larger, that doesn't give us any trend as to whether the y's will tend to be below the line or tend to be above the line or tend to be farther from the line or tend to be closer to the line. So we say, overall, there's no particular trend in the residuals, that is, after we take out the linear relationship, and that tells us that the linear relationship really is telling us something about the relationship between x and y. Now let's look at a second example, again an example that I just created, and here again it looks like the data is pretty linear, that is, there's a linear relationship between x and y, and again we can put in the line of best fit, and here it is, and it appears to describe the data fairly well. But if you look closely, you might already see a little bit of something unsettling. That is, it looks like the data points are above the line at the beginning and end at the left and right sides, and they're below the line in the middle for the most part. And again, we can see this much more clearly if we graph the residuals. So here's a graph of the residuals. And we can see now that it's fine that the points aren't all on the line and some are above and some are below. But what's concerning here is that when x is small or x is large, the y's appear to be, for the most part, larger, that is above the line, so the residuals are positive, whereas when x is somewhere in the middle of the values, then the residuals tend to be negative, which means the y values tend to be below the line. So there's sort of a trend here. The residuals shouldn't have any trend anymore if it's truly a linear relationship, and yet they have a trend. They go from larger to smaller to larger again. So that's okay, but it means that in this case, the linear relationship is not describing the whole story. And indeed, I created this example by putting in a quadratic relationship between y and x. So that's why we got this distinctive pattern that isn't captured by the linear relationship. Now let's look at a third example. In this one, again, it looks like the dots are pretty much following a linear relationship. And again, we can put in the line of best fit, and it looks like it describes the data fairly well. But again, if you look closely, you might see a bit of a trend in that for smaller x values, the y values appear to be very close to the line, whereas for larger x values, the y values appear to be farther from the line. And indeed, we can see this again by doing a graph of the residual values. And here it is, and we can see that the residuals tend to be quite small, whether positive or negative, when x is very small, but as x gets larger, these residuals are either quite large or quite small. So again, that's not such a bad thing, and it still might be useful to have the line of best fit, but it also tells us that there's more to the story, and we can't just describe the relationship between y and x by a purely linear relationship. Now let's consider a final example, Namely, let's consider that example of the life expectancy of various countries and territories around the world as a function of their GDP per capita. Now, we've seen this graph before, and we fit the line of best fit like this. And on the one hand, it looks like this line does capture a lot of the relationship, and indeed we found that the corresponding r squared value was a little more than 0.4, which is fairly good. But at the same time, just by looking at the graph, we can see it's not really linear shaped. It's got this funny curve or arc in it, and the linear relationship really isn't capturing the whole story. We can also see this if we graph the residuals, and here's a graph with the residuals, and we can see now, again, it's fine that some are below the line and some are above the line, but we see a very striking pattern. The countries with the smallest GDP per capita are mostly below the line, and then they kind of all go above the line, and then the really rich ones go below the line again. So this is certainly not a case where we have a great linear fit because the residuals don't show any trend. Here's a case where the residuals show a lot of trend. So in a case like this, if we wanted to improve the situation, one thing we could try to do is transform the variables. The most common transformation, and often a very useful one, is to take a logarithm. So hopefully we all remember logarithms. They're often done as natural logs, that is in the base e, but that scares some people, so let's just do them as base 10. And let's remember that if the log base 10 of a equals b, that means that 10 to the power of b equals a. So it's sort of an inverse of taking exponential, or of multiplying lots of 10s together. So now suppose we take the logarithm of, in this case, the GDP per capita, since that varies to such extreme values. You could take a logarithm of the life expectancy instead, or you could take a logarithm of both, or you could use other transformations like squares and square roots and so on. There's all kinds of things you could do. But for now, let's say, well, the GDP per capita varies to such extreme values that let's take a logarithm to kind of smooth things out. So we'll replace the GDP by the logarithm to the base 10 of the GDP. Now if we graph life expectancy in years as a function of the logarithm of the GDP per capita, then the graph looks like this. And we can see now that, again, there's dots all over the place. It's not a very simple relationship, but it does kind of look a little more linear. Once again, we can use the usual formulas to get the line of best fit, and here it is. And it appears to describe the data fairly well, maybe a little better than it did before. Indeed, we can check the r squared, the coefficient of determination, and in this case it's equal to about 0.658, which is even higher, a fair bit higher than the 0.4 that we had before. So we say that's good. Once we took a logarithm of the GDP per capita, then the linear relationship appears to describe it even better than it did before. But we can also look at the residuals again. So here's a graph of the residuals, again, when we're looking at the life expectancy as a function of the logarithm base 10 of the GDP per capita. And in this case, well, I wouldn't say it's without trends. That is, you can see that still the poorest countries tend to be below the line. The medium countries tend to be above the line. A few of the richer countries tend to be below the line again. So there's a little bit of a trend going on, but I would say it's far less pronounced than the trend was before. And I would say this is a much better fit. So we can say that the life expectancy seems to fit fairly well as a linear relationship with the logarithm of the GDP per capita. Now, once we do a transformation like that, we have to be able to understand how to interpret it. In this case, the slope was equal to about 14.93. But what does that mean? Well, that means if the logarithm of the GDP per capita increases by 1, then it tends to be that the life expectancy increases by about 14.93 years. But if the logarithm base 10 of the GDP increases by 1, that's the same as the GDP per capita being multiplied by a factor of 10. So what we can really say from this is that every time the GDP per capita is multiplied by a factor of 10, then the life expectancy in years is increased by about 14.93 years on average. Or the other way around, if the GDP per capita is divided by 10, then the life expectancy is decreased by about 14.93 years. Or for that matter, if the GDP per capita were multiplied by 100, then that's like multiplying by 10 and then multiplying by another 10. So the life expectancy would increase by about 14.93 plus 14.93 years. So in this way, we've discovered a relationship between the GDP per capita and the life expectancy in years, but it's not really a linear relationship in that way. It's a linear relationship between the logarithm of the GDP per capita and the life expectancy. So we'll see fairly often that transforming variables can sometimes make the relationships more clear and indeed make a linear relationship be a better way of describing the relationship. So that's good, but we do have to be careful to interpret the final equation in a way that makes sense in light of the transformation that we've performed. So in this way, we see that when you're considering a linear relationship, you should do things like look at the graph. You should think about whether the residuals appear to have trends, which is bad, or they appear to be free of trends, which is good, and means the linear relationship really does describe the relationship. And you should also think whether there's ways to transform the data in order to make the relationship linear and therefore a more accurate description.